Okay, so um, all right. So wait, I hope that I can handle. I need to talk while keeping aware of if anybody's joining. So today we are going to talk about sinusoidal modeling. Okay, so sinusoidal modeling, the best way to explain that might be to run you the program first. Okay, so let me mention that all the materials are already on here in eLearn. So here you can find some example files and as well as the starting code. Okay, so please come here to download all the files. But today, let me just first go through the code. Okay, so by the way, did you hear the music I was playing before the class began? Did you hear the music? I'm just trying to make sure that my computer is broadcasting the sound. Who's playing the music? Let's see, it's been a while. So do I open the chat? Yeah. Yes. Okay. So, all right. So I appreciate if you just openly say yes, because on my screen, I need to toggle around different windows. So if you just type yes, I might not be seeing it right away, right? So anyway, so 吴全燕, okay. So today I would like to first show you that in this starter code, you will be reading a file, of course, and then when you run the file,
draw every outer line first, then fill in the interior.
The system plays the sound, the sound example that we are going to analyze. And here you need to answer two questions. The first is how many peaks to track. Let me just briefly mention that sinusoidal modeling is about tracking peaks in the spectrum. While the spectrum is changing with time, the peaks can also move. But anyway, so let's say we would try to track 20 peaks all at the same time. And then this program also allows you to specify a time expansion factor. Okay, so you can play slowly or you can play faster. So let's say the expansion factor is something like 1.7, which will be slower. And then when I hit enter, it's going to analyze signal and then it will play back the signal as well as show you the spectrogram.
Draw every outer line first, then fill in the interior.
All right, so I hope you've heard the result. It played back slowlier, and this is the graph I want to show you. So I spent some time to try to figure out how to put the dot, how to overlay the result of peak estimation on top of your spectrogram. Okay, so again, you probably by now you know what the spectrum is and spectrogram is. Here again, the dark parts are where the energy is concentrated, right? So here, the program is what it's doing is to put a green dot, wherever it finds a peak over there. Okay, so you see that this is kind of sanity check to see that okay, the peaks that's been identified as the right location. They're exactly on where the energy is concentrated, where the peaks are. Okay, so so this is to show you that this is the situation. Sinusoidal modeling, the first step of all is to identify peaks, because peaks, what does a peak in the spectrum mean? A peak in the spectrum just means that the energy is concentrated there is it could well be there is a tone, there is a sinusoid. So the peak of the spectrum tells us that there should be a sinusoid exactly at that frequency and with that magnitude. So this is what sinusoidal modeling is about. And so you'll see that we'll go through today's lecture that it's rather, once you obtain, you calculate all where the peaks are, then you can choose to play back at whatever speed you want. Play faster, play slower, because the location of the peak actually is a representation of the sound. So that's the idea. Okay. Again, please feel free to interrupt me anytime. Yeah. So with that, I would like to switch to my PowerPoint. All right, so today's short lecture is the topic is sinusoidal modeling, and today is an introduction. And so please remember that probably in the beginning part of this semester, we talked about a kind of a general framework for blockwise audio processing. So in the input side, you would typically take a blockless signal by multiplying the signal with a window, and the window does not have to be rectangular. And then we use fast Fourier transform to go to the frequency domain. Capital X represents the Fourier transform with lowercase x. And then we just vaguely say that in the frequency domain, you can do whatever manipulation you feel is the right thing to do. And in the past, we have tried linear prediction. We have in the previous homework, mini homework, I asked you to simply do filtering by multiplication in the frequency domain. So those are certainly some kind of manipulations. And then to produce the output, you pretty much do the opposite. Okay, just invert every block, Fourier transform, inverse transform, windowing, overlap, add. So these are like this is like a nested structure with like your manipulation being the centerpiece of consideration. But today I want to mention that the block diagram for sinusoidal modeling is slightly different. Okay, so what is different is after the manipulation. Okay, so in sinusoidal modeling, our manipulation is going to be to obtain a representation. And this for this representation, we call it the sinusoidal representation. Basically, the green dots you were seeing. Okay, we start from there. So those are so in this under this general framework, yeah, there's a certain manipulation part is to identify where the peaks are. But then after that, the synthesis part, strictly speaking, does not you do not use inverse Fourier transform, at least not as I know of. Okay, so we'll later see. Yeah, today I actually freely gave you the synthesis code. So you see that in there we actually don't do the inverse transform. Okay, but we kind of directly synthesized out from our representation that is given by sinusoidal modeling. Okay, so that's kind of a general framework to recap. And the next slide. So I want to also mention that there are a few issues to consider when we talk about extracting to identify where the peaks are in the frequency domain to estimate the sinusoidal frequency and amplitude. And there are certain like performance limitations, and two issues I would like to raise to bring to you briefly here. The one issue is called the issue of resolution. The other issue is the issue of accuracy. I want to, at least within the scope of this course, I want to say that these are two different terms and they have different meanings. Okay, resolution is in Chinese would be 解析度, 解析度, and accuracy is 精确度, how accurate you can estimate the parameters. So let me just go through the points quickly, and then we'll dig into more details. Resolution, when we talk about resolution, the scenario is that in the spectrum, there could be multiple peaks at different frequencies. Also, so yeah, in the spectrum, you'll see most of the time you have harmonics, or if you are talking about two people talking simultaneously, sometimes even the peak can overlay. Okay, so generally, we often have multiple peaks, and they can interfere. And the situation that they can interfere because of the uncertainty principle, sort of. So the general principle is that you need to choose a window type of the window and also the length of the window, so that you can use the window to resolve resolution about resolving. You can resolve two peaks at two different things. Okay, so there's one peak, there's another peak. If they interfere, what is the minimal length of window, for example, for you to be able to resolve the two peaks? And the answer, briefly, is the rule of thumb here is that if you want the resolution to be delta omega, so if you want two peaks that are delta omega that much apart in the frequency, that are separated apart by delta omega, omega being the frequency. So at least this resolution is inversely proportional to the length of the window. Okay, so O being denotes order. So it's the resolution is the minimal distance in frequency that you can separate is basically 1 over the length of the window. Okay, in that order, sometimes 2 times that or 4 times that, depending on the type of a window. So that's the general rule of thumb. That resolution in frequency is inversely proportional to the length of the window. Okay? Whereas in accuracy, this relation is different actually. So what is accuracy? Accuracy is when we are concerned about signal in noise, right? So anytime you measure a signal, there's always plenty of noise around. And so when we try to estimate the parameter of a signal in noise, then is there a kind of a theoretical limit for the performance? And the answer largely is yes. Okay, so this is itself a rich topic, and if you are super interested, you should check the buzzword of Fisher information and Cramer-Rao lower bound. You should check that. Is anybody joining in? Okay, I need to approve 2 more people. All right, thank you for joining. And my apology for the wait. 寿斌跟张俊行啊，好 ，so you guys are here more. People are. My friend have not invited in class. Will you invite him? Thanks. 泽广哈 yeah. It might be hard for me to teach and yeah. Anyway, this lecture is going to be recorded. I'm recording it, so I'm answering 泽广 so yeah. Anyway, so I need to continue. Yeah. Anyway, yeah. Sorry for kind of. We have a lot of material to cover today, more than 20 slides. Okay, so I wish yeah. Otherwise I'm gonna have a delay. Anyway, so okay, so that's the rule of thumb. Fisher information Cramer-Rao, yes, there is a theoretical limit as to how accurately you can estimate a parameter, be it a frequency or amplitude of the sinusoid or any other thing, phase. There is a theory behind that, but in this homework, we are indeed going to estimate the peak locations and magnitude, and we are going to go through a more of a practical approach. So I will propose to you, and this is the content, the thing that you need to implement for this homework. I'll ask you to implement quadratic interpolation of log magnitude spectrum, basically. Okay, so we'll talk about that, and that's to deal with the issue of accuracy. So 2 different issues. And let me also mention maybe right here that the kind of frequency estimation, the theoretical bound, the performance bound for the estimation error is that the error will be proportional to this the length of the window to the 3½ power, 1.5次方 3½ power. So that's the kind of the scenario. Okay, so to begin, so let me give you an example. So I'm pretty sure that everybody knows what this is. That's the buttons for your telephone, and the kind of the way telephone numbers are encoded in the network is by 2 tones. I'm not sure if you're aware of that. Each time when you press a button, okay, what you hear is a combination of 2 tones. So I like to use this as an example to explain different situations when we try to estimate exactly the frequency of those two tones. So let me say I did some homework. The tones actually, so for each row, the first tone is encodes which row is the button, okay? And they have lower frequencies, and the higher frequency tone encodes the column. So by so each button has a unique combination of two tones as two different frequencies. For example, number 5 is a combination of 770 and 1336. Okay, so that being said, we can try to listen. Let's listen to 770. So that is 770, and then this is 1336, right? And so by now, can you try to imagine what if you put the two tones together? Can you try to imagine that? Can you try to imagine that? So, and the combination of the two tones will be just what you hear, how you hear when you press 5. Okay, so I'll show you this now. 5. So that's 5. So we are all very familiar with that. So, but now the question is, all right, so this is like you have a touchpad and you can press the tones, but in the decoder, how does the network know which button is being pressed down? And please note that this is way before even computer popularized. Okay, so for the telephone network, there's no like embedded system that actually transmit the logic of which button has been pressed. Everything has to be communicated through the telephone line, right? So you see that these are sound. When you press number 5, the sound of two sinusoids being played together is transmitted through the telephone line to the router. So then the question is, how does the router know which button has been pressed down? So maybe over there, there's some DSP. So that's kind of a scenario, a very practical scenario that indeed, in this figure, we are looking at iPhone Chun. Okay, OK， 谢谢许竹君加入啊。So in this figure, we are looking at the waveform of these two tones, the combination of these two tones. And so the idea is that what if we window the signal with this bell-shaped window? With this bell-shaped window, we window that and then perform FFT. Are we going to see exactly a peak at 770 and another peak at 1300? And if so, then we can just simply identify where the peak locations are by finding the maximums. And then simply, then we know which button is pushed. Okay, any questions so far? Good, yeah. So that's the idea. So now, but before we show the spectrum, let me make a few derivations. So when we say that we window the signal, which is a combination of two tones, and the combination of two tones can be expressed as two-component cosine with frequency f1 and f2, maybe starting phase, some random phase, phi1, phi2, as well as the magnitude a1 and a2. And they are the real part of complex exponentials, which means that this thing here is a combination of one complex sinusoid, the second complex sinusoid plus their complex conjugates. Okay, so if we know your DTFT well enough, you know that the Fourier transform of that would be simply this magnitude times a delta function, a copy of the Dirac delta function at exactly omega 1 and omega 2, where omega 1 and omega 2 equals to 2 pi f1 and 2 pi f2. Okay, so that's kind of a brief derivation. But then now the question is, this is like DTFT. This is supposed that if the signal lasts forever, if n runs from minus infinity to infinity, then we have a spike, a delta spike in the spectrum. So the next question is, then how about when we talk about short time Fourier transform, when we window the signal with a finite length W of n, what would happen in the frequency domain? And the answer is we'll see a spectral copy of the Fourier transform of that window. Okay, So the x, after multiplying it with the window and you do this, again, do the DTFT, the result is still this amplitude A1, A2 corresponding phase, as well as a copy of W. Big W is the what? The Fourier transform of small w. Okay, so this is the Fourier transform of a window. So we will see a copy of that shifted to this frequency, shifted to the frequency of the respective tones. Okay, so so that means keeping this mathematical expression in mind. For example, if the window is Hahn window of length 20 milliseconds, indeed, we're seeing one copy of the transform window and the other copy of the Fourier transform of the window exactly at the right frequency, 770 and 1300. Okay, so that's one example. So this look easy, right? So in order to look at the spectrum and know which button is pressed, you now have a clue. Just identify the peak and find out its frequency. So it's pretty straightforward. And here, I want to talk about the issue of spectral splattering, okay? So this is the difference between Hahn window and rectangular window, using them to acquire a block of signal. So you know, so you please note that now I'm playing, no, this is in, wait, is this in, yeah, this is in linear scale, by the way. Okay, not yet, not even in log scale. But in linear scale, if you look at the difference between Hahn window and rectangular window, the results, you see that first of all, the peaks are still at the significant peaks are located at the right location for sure, for both windows. But the difference is that, first of all, Hahn window results have a wider main lobe. The width of this is called the main lobe. The main 主要的 lobe is like a petal, 是花瓣的意思。So the main lobe versus in rectangular window, if you use that for analyzing a signal, you see a lot of extra peaks, and that could be problematic. That could be problematic because when you use the rectangular window and look at the magnitude spectrum, how can you be sure that there actually are only two sinusoidal components? Maybe this is itself represent a peak also. Maybe even the second peak next to the first peak and so on. These are the side lobes, and they can be confusing, right? Imagine that you're actually looking at the spectrum of a real piece of music, a short frame, and you see peaks everywhere, and which ones are fake and which ones are real. That becomes a hard question to answer. So generally, we don't recommend using rectangular window, okay? And so we use Hahn window because it is well known that the side lobe ratio, the side lobe suppression, main lobe to the ratio of main lobe to side lobe is much higher in Hahn window than for a rectangular window. Okay, so this extra the presence of extra peaks here, sometimes we call that issue to be a spectral splattering. Splattering means that like a puddle of water, 如果有一滩水啊 and you step on the puddle of water, 那个水会怎么样？ The water is splattered, 溅得到处都是。So this is a kind of a description. These are unwanted effects that we don't want to be confused due to their presence, due to the presence of spectral splattering brought to you by rectangular window. Okay, and so now, so that's 20 milliseconds, but rectangular window, right? So also there is the issue of choosing the length of window. Okay, we know by now. I hope that it becomes straightforward to you that when we have a longer window, we have narrow peaks, shorter window, wider peaks in the spectrum. So here is the contrast between 20 millisecond window versus 2 millisecond window. You see that the 2 millisecond window results in a broad peak in the frequency domain. Okay, even though one of them is still around 770, the other is around 1300, but they are pretty wide. So there's a certain kind of there is a kind of uncertainty in here. Okay, and also again we are seeing the side lobes. So then the question is, what is the kind of the preferred length? How long do we need the window to be in order to separate 770 from 1300? And the answer, as I mentioned briefly I just mentioned briefly, since the main low width in the spectrum of the window is inversely proportional to the duration of that window, then we needed to use a sufficiently long window so as to resolve two spectral components. And the rule of thumb is that that separation is that minimal separation is inversely proportional to the length of window. And for example, let's say in this case, we press down the bottom 5 and we want to resolve two frequencies that are apart by 566 Hertz. So the inverse of that is around 1.8 millisecond. So that means that your window, at least, to say the least, at least has to be so long. At least it has to be 1.8 milliseconds. Usually we require 2 times, 4 times longer to play safe, okay? So I want to pause a bit to make sure that this is understandable. Is that all right? Any question right here? Okay, so let me still move. Please feel free to interrupt me anytime, as always. And so today is the beginning of a series of 3 homeworks. Okay, the first homework is this homework. The second homework we will be dealing with synthesis, and the third homework you will be dealing with sign plus noise decomposition. And so. So in this slide, now, so we've talked about the resolution issue. Now comes the noise issue. We know that in any measured signal, inevitably, okay, 无可避免的, there always is the noise. And the noise generally affects the accuracy of your estimation, even if the resolution is good enough. Okay, even if you have a long enough window to resolve 2 peaks, but noise is still a separate issue. So let's say, for example, if the combination two-tone is as the dashed blue line is showing, and due to the additive noise, you see the result is noisy. Now, we all see that all the time. Therefore, in the spectrum, even if we use a good window with the right length, indeed, we are seeing a peak at 770, another peak at the right locations. But then one issue is that one obvious issue is that we have like spurious peaks that we are not sure how to handle, because these are just noise. We know that is noise, but what you get is just a noise contaminated copy of the spectrum, then it's really hard. It's really not a straightforward. I mean, it is something that we need to be serious about, okay? And so here I put a question mark here, okay? Because also because of the noise, the peaks are generally going to drift away from the right answer, okay? It might be 760, for example. There might be estimation error because of the noise. Right, so that's a clean version versus a noise contaminated version. So a few more things I want to again emphasize that resolution and accuracy. By now, I hope that it's been clear that accuracy is the issue of noise, whereas resolution is the issue of interference between concurrent sinusoidal components. Okay, and so again, a summary resolution. That the minimal separation is inversely proportional to the length of window, whereas accuracy, the noise estimation error incurred by the presence of noise. Noise 造成的这个误差啊 this is an error. Estimation error, if you take the variance, I should have put in var here. So the variance of estimation error, in this case, frequency estimation error square is proportional to the third power of window length times, what is this? Sigma squared divided by A squared. That's the noise to signal ratio. A divided by sigma squared. A squared being the amplitude square, sigma square being the noise variance. And actually this denotes so the accuracy, the estimation error square is inversely proportional to SNR. The larger, the better, right? Also, the estimation error square is also inversely proportional to the third power of the window length. And that's the difference between resolution issue and the accuracy issue. So I want to bring this to you. Okay, so now we talk about the kind of performance limitation, right? this is kind of the lower bound, the best case scenario. So then the question, the kind of an academic question is then, how do we design a frequency estimator that approaches this limit that has almost as good a performance as the theoretical limit, okay? And a very straightforward way, as we will take a look, is called the quadratic interpolation in the log domain. And here's a reference. It's in ICAS. Okay, Smith is my advisor, Julius Smith, and Abe at that time was visiting from Japan, and he worked with Smith. So they proposed that this very simple method, rather simple method, turns out to be pretty robust. Okay, so let me show you what is this. What do we mean quadratic interpolation in the log domain? Okay, so now comes that analysis. Okay, so this is kind of a result. Okay, a result of looking at the spectrum of this sound, which is a trumpet. So this is taking one frame of the trumpet sound, and then just take the Fourier transform. Okay, you see there is the fundamental frequency and the harmonics, as well as some spurious kind of unwanted peaks. Okay. Unwanted peaks. So the issue is now we need to, how do we ignore the unwanted? How do we ignore this? How do we ignore even that and that and so on? So I'll leave this as a kind of open question to you. So there must be a way for you, for better or for worse, you need to be able to make a decision, make your judgment, okay? Which peaks in the section are actually prominent and they should be kept, whereas others might be some noise because of noise, okay? But that's kind of general case. So here, sinusoidal modeling's first step is very straightforward, to find peaks in the spectrum, okay? Wherever you see local maximum, just find it. And then the second part is then to refine your estimation of the local maximum. Let me explain this first, and then I'll come back to zero padding. Okay, so quadratic interpolation is that basically you fit a parabola. This you fit a parabola. You fit a parabola near the local maximum. Okay, and then you just use the apex of that parabola as your the estimated amplitude or magnitude, and also the location of that parabola in general would not be on integer frequency, frequency grid points. They could be a fractional number. Okay, 有小数点的部分. So you also use that as your estimation of the frequency of the sinusoid. Okay, very simple idea. And so, but here in the flow, after windowing, I do suggest padding zeros. Okay, so what do we mean zero padding? Zero padding means that now you have a windowed portion of the signal, which might be a certain length. And you have done that in the previous homework, the mini homework, and the purpose for zero padding there is to avoid a cyclic convolution artifact after what? After multiplication in frequency domain. Okay, so that's kind of filtering application. But here we also suggest zero padding, and the very reason is because that we know that the kind of resolution. Okay, this is not the resolution. I mean the number of points we are looking at the Fourier transform is exactly the same number as the length in the time domain, right? So even though adding zeros does not increase information, there's a benefit of that when you add zeros, then you are looking at more point of the DTFT of the signal. Let me say that again. So adding zeros is not giving you extra information, but then after Fourier transform, you can just right away you can look at more points in the frequency domain, and more different frequency locations in the frequency domain. So it suffices to say that by appending zero in time, and this is a theorem, by appending zeros in time, we are doing an interpolation in frequency. Okay, so zero padding already give you more points to be considered the peak, and then from there you find the maximum and then fit the parabola near that maximum. That's the step of the kind of in your homework. I asked you to do this, right? So here are some details about quadratic interpolation. Suppose that we have 3 points, and we know that so here I'm shifting the origin without loss of generality. I'm saying that 0 means the location of a local maximum in the magnitude spectrum, okay? And so in here, if we denote the height of these 3 frequencies as L0, L minus, and L plus, L0, L minus, that's a height, okay? And then to fit a parabola, the parabola has this formula, right? Ax squared plus bx plus c, and which can be factorized as a times x minus q squared plus L hat. So I hope that, first of all, let me mention that since we are fitting near a local maximum, this A is always negative, okay? Actually, A in terms of L, the height A has this expression, okay? And A, you can see that A is always negative because it's a concave down. It's the peak is pointing up, right? So first of all, A is always negative. So when you factorize a Q, when you calculate ABC, which are given by the formula, you can check that. I've made the derivation for you. You see that Q is equal to, Q is the shift. Q is the location of the estimated peak relative to the frequency of the local maximum, right? So you have a shift of a B divided by 2A, and there's a minus sign. And also the kind of refined peak is going to be generally larger than the actual peak here. So this peak is larger than the maximum spectral sample, for sure, because we are fitting a parabola, okay? And that the apex should be no lower than the largest sample here, right here, okay? So we have a revised estimation of the peak, that's the apex of this parabola, as well as the location, a revised estimation of frequency. That is 0, this frequency plus this much times. This is, by the way, everything here is normalized to like 1 means the distance between 2 adjacent spectral samples. So you need to figure out the normalization. But otherwise, the idea is very simple. It's simply to fit a parabola near wherever you see a local maximum in the magnitude spectrum. Okay. Any questions so far? Okay. All right, so let me continue. So we haven't talked about window. Okay, so here I'm recommending to use the Blackman window. In my starter code, I use the Blackman window. Blackman window is even wider than the Hahn window, and it has a better side lobe suppression ratio, higher than 50 dB. Okay, here you see the main lobe, and the highest main lobe is below 50 minus 50 dB, and this helps to suppress the spurious peaks that we mentioned. We can hide them beneath what is called the masking threshold. Okay, so and now here is an example of tracking the peaks as the frame as the music proceeds. Okay, so let's listen to the sound file first. Madonna mia cara, mi canzone. Right. So on top in figure A, what we're looking at is the result of peak finding. Okay. For every frame, this m, little m stands for the frame index. So for every frame, we are looking at up to a few peaks. And if we just plot the location, put a cross at wherever we find the peak in that frame, then this is the result. And I hope that we can all agree that, at least to our eyes, what are we seeing? We are seeing like 5 long-lasting traces, right? Can we agree on that? 我们都看到了5条往右延伸的东西嘛。We will look at 5 long-lasting trajectory. Okay, 1, 2, 3, 4, 5. And also, you might have guessed that they are roughly equally spaced because the first one might represent the fundamental frequency, and as well as here you see vibrato. Okay, there are vibratos. Okay, so it makes sense for our eyes to tell us that. So in our brain, almost automatically we see 5 traces. But then the question for your next homework is really, how do we teach the computer that there are indeed 5 trajectories that run from the beginning to the end? Okay, so that could be quite tricky, and we'll leave that to the next homework. Okay, we leave that to the homework. So it's not all that straightforward to kind of connect the crosses, connect the dots, so that we can the peaks can form trajectories. Okay, it's not all that trivial to do this dimension. Okay, but that's the next homework. But in this homework, I want to also briefly talk about synthesis. Okay, so we've talked about finding the peaks using quadratic interpolation, the log of magnetic spectrum. But how about synthesis part? The synthesis part means that we need to take that representation. So suppose that we already have trajectories. Okay, so suppose that then given the trajectories, how do we synthesize the sound? And there are 2 methods. Okay, so the basic idea. So let's introduce a few notations here. Let's say that if we have a trajectory, one trajectory, just one curved line. Okay, one trajectory. So we will be in sinusoidal modeling. We will be recording the amplitude A and the frequency F of that trajectory. So not only its frequency can change, its amplitude can also vary to account for dynamics, right? So let's say the sequence of AM, M being from 0 to M big M minus 1, and F. These are denotes the sequence of the detected frequency as well as the amplitude. Or should we say simply call them the amplitude and the frequency envelope of a trajectory? Okay. So given a trajectory, just one simple line, such as this one, then our goal is like for each trajectory, we synthesize a signal in this form, a signal of which the phase is constantly changing, as well as we also allow the amplitude to change instantaneously. And so the idea really is here, by controlling the amplitude and the phase with precision. If you know exactly how you want them to be, then you might be able to operate an oscillator. Basically, we are playing with an oscillator, okay, by controlling its phase and amplitude with precision, okay, 精准的控制, so that's the idea. So, and there are 2 methods I'd like to bring to you. And the first method is actually from my dissertation. Given the trajectory, given the amplitude and frequency envelope, here the idea is to use window for signal reconstruction. Okay, so the idea is that we are going to place a window copy, and this window needs to satisfy the Kohler condition, such as the Hahn window. Okay, and you see my code, I do that. So W, let's say W is the Hahn window, and so the idea is that so here one Hahn window, the next Hahn window, the third one, the fourth one. So let's use this as an example. Okay, so here AM is from 1, 2, 3 to 4. It means that you can roughly reconstruct the amplitude varying effect. Okay, it's changing from one frame to the next, and to the next. When you add them all together, and also inside the amplitude there is a cosine part. The cosine part has an oscillation. That's what I was talking about, controlling the phase with precision. And how precisely? First of all, we want to put F here, right? Because F means that in the analysis part, we have figured out that right at this moment, there is a sinusoid of this frequency that's present in the original signal. So we want to put it back. And then, so that's the frequency. And also you want to take care of the phase, okay? From one frame to the next frame, the frequency. So here I use the colors to kind of encode, to show you the color. Different color means different frequencies. I hope that it is intuitive. So as the signal is changing its frequency ever so slightly, how do we update the phase? This is important. We want to update the phase by this kind of this is in my dissertation. So I suggest that the phase increment should be 2 pi times the average frequency times the length of the hop size. Okay, that's my suggestion. Okay, so here F is in the unit of hertz. Okay, any question here? You are not asked to implement this. You'll see this in my starter code, but I want to kind of talk about kind of underlying the thoughts I put in behind this formula. Okay, any question? Are we okay with this formula? And another method I would not, this time I will not emphasize, is that you can theoretically even do even better by allowing the amplitude to linearly change from a previous estimated value to the next estimated value by linearly changing it between in the time in between. Okay, changing that, I also linearly interpolate the frequency, and then update your phase sample-wise update. Please note that here the updated phase is only frame-wise. So this method has the advantage that the computation load for the phase update is smaller. That computation load is smaller than sample-wise update of the phase. Okay, there might be some benefit of this, but I'm not going to emphasize that in this semester. All right. So finally, there is a final demo. So this is the last slide I want to show today. So note that in sinusoidal modeling, what we extract is a representation trajectories, right? Trajectories. First of all, I forgot to mention that you do need to superpose all the sounds synthesized by each trajectory. Each trajectory gives you a sound, second sound, third sound, and you need to somehow add them all together. Okay, and we'll do that in the coming next 2 homeworks, not this one, but the next 2 ones. But here I want to tell you that, share with you that we have shown time playing back at a different speed. But in the meanwhile, once you obtain the trajectory, you can also feel free to not only to stretch or compress them in time, but also to shift them in frequency, right? So this automatically gives you an implementation. You can just shift the frequency before you play them back, and this is the result. So we are going to be listening to a bird call. So once you extract the sinusoidal representation for this sound, then you can choose to play it back at 1 octave lower and slower. And so it becomes sort of a larger bird versus the original. Okay, so so that's all I want to say as an introduction to sinusoidal modeling. Any comments, any question, anything sort of unclear? I'm running out of time slightly, right? Oh, not yet, actually. I'm doing fine. Yeah, we have time for maybe 2 questions. Or if you don't have a question, let me ask a question, right? So in this bird example versus just beside the change of speed and pitch, what other difference did you notice? Do you notice any other differences? Any other differences? Or should I stop recording? 对话 background noise. Yeah, 谢谢许竹君. Oh, thank you. That's one thing. Okay. And why? But how about background noise? 竹君，你们分享一下. What did you notice about the background noise? Is it better? Is it worse? Or what did you notice? Some information is discarded. Okay, 谢谢刘婷. What kind of information is discarded? The output eliminates the noises. That's
the information other than the peak frequencies.
Yeah. Right. So you can argue. So actually, if I remember correctly, I created the example by simply tracking one peak. Bird call is like predominantly one peak. It's quite different, unless you're talking about Yingwu, the parrots. I would love to analyze parrots. But anyway, so yeah, a lot of things are eliminated, and you please play with the sound files. And yeah, okay. Thank you for the comments, the two of you. And so that's about it. So by the way, let me also mention that, actually, we can stop recording now. Let me first stop sharing. Okay. And I will stop. Yeah. So I want to also just simply mention that because in this homework you are asked to implement the analysis part by yourself. Okay. So if you ever wonder what the right answer should sound like, I have also uploaded a few examples. So in the e-learning, you will see a few examples of the kind of correct output. So you have a kind of expectation. If you reach any level, it's not going to be perfect, right? But if your sound quality is roughly the same level quality, then you're doing fine. Okay. So with that, I'd like to conclude today's introduction. Thank you for joining. I'll hang out for a little more, but you may feel free to dismiss now. Thank you. Bye bye.